Okay. All right, thanks so much for the invitation to share some of my research on clouds and climate change. This is where we're going to go today. I'm going to tell you about the cloud problem, share a taste of what we do in my group about hypothesis testing in atmospheric science, and share with you some new hot off the press predictions about climate change that we're just beginning to learn from new technology, and then talk about the special clouds that we live next to. But first I want to tell you about me and how I became a climate scientist. So I'm from Canada and I started studying physics. I'm a physics nerd. I love physics. I love learning about the cosmos, and I started in astrophysics, but I didn't really enjoy my first summer job doing that. And I was 21 years old and took a disillusioned trip around the world and went hitchhiking around Australia, and I ended up here in Bangladesh. This is a picture from space of the floodplains of the river Ganges, and it's a beautiful place. It's a special place for me. It's important to me. I was born there. This is me in 1981. I just had my first kid, and my dad brought this photo down. It was a kick to see it. This is my dad and my mom. This is my family. And they were doing some volunteer work in Bangladesh at the time. I was always curious about it, so when I was 21, I went back and checked it out for myself. And it really struck me. It's an amazing country. It's an amazing place. And I remember getting back from this trip around the world halfway through my physics degree, wondering if I was going to stick with it. And being a little unsatisfied with my dabbles in astrophysics. And then I realized there was this other physics problem that was really important to a place that matters to me. And this is a projection of sea level rise in Bangladesh, showing inundation. A huge fraction of Bangladesh is really close to sea level. It's a very low-lying country. And so it doesn't take a lot of sea level rise. Even 1.5 meters is projected to displace 20 million people. And we still don't know a lot about what exactly is going to happen in this part of the world and the risks that people in Bangladesh and other places face, not just from sea level rise, but from the storms that cause flooding and damage that are linked to sea level rise. And so that's part of my story about how I came into the field, and I sort of transitioned to thinking about climate. And first I thought about ice sheets. I did a master's looking at ice sheets. Ice sheets are related to sea level rise. But as part of that work, I got a taste of how modern tools that are used to predict climate change work, the numerical tools that we use to make climate predictions. And you don't have to use these tools for long before you come to appreciate the cloud problem. So most people who use the tools of climate prediction know about the cloud problem. And that's what I'm going to talk to you about today. Here's a quote from the IPCC. So this is, the world authority that synthesizes our scientific understanding of climate change every 7 years. This message has been there for every report, 7 years ago, 7 years before that. Cloud feedbacks are known to be the largest source of uncertainty in our modern predictions of how climate change will happen. And so, naturally I wanted to work on them. So I did my Ph.D. at UC San Diego, focusing on a new technology that is trying to make clouds more explicit in climate models. I'm going to talk to you about that today. I worked on that in my postdoc at the University of Washington. That's a place where there's lots of atmospheric scientists and cloud experts applying this technology to analyze storms in the Indian Ocean near Bangladesh. And ESS is now my home, and it's kind of my perfect home for some of the reasons that Ken mentioned. It's home to people like Eric Grignot, who do ice sheet research that's connected by, if you've seen that Vice episode, explicitly to sea level rise in Bangladesh. And I really like being at ESS because I really like that a lot of my colleagues share this kind of global perspective and motivation for the physics that we like to study. So let's talk about clouds, the cloud problem. So the cloud problem means for climate change huge error bars on important questions like how will weather change where I live in the future, and also for the world, how much will the climate change on average. Clouds are critical to both of those questions, and clouds are just really important to understand this. If you ever go winter camping, we do this in Canada, maybe you've done it, maybe you haven't, you're really happy if a high cloud rolls in, okay? Because it means it's going to be a warm night. Clouds keep you warm. It's counterintuitive because if you go to the beach and the clouds roll in, they cool you off. Clouds are important because they change the way you feel. They can warm you up, they can cool you down. Obviously, how they respond to climate change will affect global warming. They could amplify it, they could dampen it, depending on which clouds do what. Clouds are fundamental to how the planet works too, okay? The Earth is a planet floating in a vacuum. It's heated more at the equator than the poles. And all the motions of the atmosphere and the ocean are fundamentally having to do with energy transport from the equator to the poles. And nature being nature leverages the most efficient ways it can find to do energy transport. And phase changes of water, clouds, are really efficient. When water evaporates from the ocean and condenses, it releases huge amounts of energy. And so clouds are tied up in how nature and the climate system move energy around. And you see this if you stare at animations of clouds on the planet. So throughout the tropics, where the Earth is heated the most and has to do a lot of vertical energy transport, clouds are constantly churning because they're part of that. And connecting the tropics to the poles, clouds are often tied up in these vortical structures that move energy poleward. So clouds matter because they're just fundamental to the physics of the climate system in general. They're complex. Clouds are really complex. It all starts like at the scale of a dust particle. At the heart of every cloud droplet is a dust particle. And the chemical composition and molecular structure of its surface matters to whether water wants to congregate around it. And then as it grows, its chemical properties dissolve and the solute properties begin to matter. And then the microphysics of how that droplet affects turbulence around it matter as to whether the droplet finds other droplets and manages to combine with them to form large droplets that we see as clouds and ultimately rain. All of these scales of physics matter. And we can see that in snapshots from space. This is a picture off the coast of Africa in the equatorial Atlantic. You can see here a massive cloud system, hundreds of thousands of square kilometers. Sometimes clouds self-organize into these amazing complexes that survive longer than the lifetime of an individual cloud for hours and hours into the night. And they're so energetic, and the energy released is so strong that it causes planetary scale wind gusts. In this case, blowing a giant plume of dust way out off the Sahara into the ocean, where you can see the dust is interacting with clouds again. All these feedbacks are involved in clouds. So you might appreciate that representing cloud physics is a really grand challenge computationally. I'm going to talk about modeling. Couple acronyms, okay? CRM, Cloud Resolving Model. That's the small, fast stuff. Global Climate Model, GCM. These are the tools of climate prediction. Small, fast, big, and slow. So the problem that we have in climate science is that we have a system that spans 10 orders of magnitude in space and time. So here's time scale getting slower, and here's spatial scale getting larger. And the tools we use for climate prediction are here, global climate models. They can resolve big and slow stuff. But the details, the clouds, live down here. We have other tools called cloud resolving models that can handle these. We know the equations we'd like to solve, and we've convinced ourselves that because if we take a large computer and apply it to a cloud resolving simulation, we can produce results like these, which resemble what you see out your airplane window when you fly to Hawaii. The issue is we don't have enough computational resources to solve those equations over the entire planet for a century. When you want to simulate the entire globe for a century, the amount of computing resources you have dictates the details you can afford to represent about those sorts of physics. So you want to know how clouds react with climate change, you have a problem. We call this problem parameterization. It's an idea that we have in our field that you have processes that occur on large scales, like a climate model grid box scale, the size of a state, which can be explicitly resolved, which you can represent accurately. And then you have to parameterize processes that are smaller than that but still important, like clouds and radiation. Parameterization is this business of trying to take things that are resolved and using them to make approximations for things that are unresolved. And the difficulty for clouds is that these kinds of processes, rainfall, how rainfall excites wind feedbacks that influence rainfall, they're really hard to approximate statistically. It begins to become an ill-posed problem. And that's why we have problems with clouds and climate models. These are problems that have lasted for decades. Climate models have the wrong intensity distribution of rainfall. They tend to drizzle too frequently, unlike the real world. Even the most simply forced cycle of rainfall in the system, which is the daily cycle of rainfall sparked by the sun, is distorted in current climate models. We have issues with and errors in the mean pattern of rainfall geographically, and we have missing weather patterns. Here's an example of a missing weather pattern that matters to Bangladesh. This is the Madden-Julian oscillation. There's India, and this is a time-lapse movie from space that shows, it's going to loop again here. You can see the day counter marching here, 29th of April, 30th. At the beginning, almost all the Indian Ocean is covered with clouds and convection. And by the end, it's almost empty. This disturbance has moved from the west to the east. It's a planetary scale oscillation of weather that's observed to happen in the tropics. It erupts about every 30 to 70 days. It's associated with extreme weather events like cyclones that make landfall. And it's a pattern that's not in most climate models. So we know climate models have some of these issues because we constantly compare them to data. We do that by comparing simulated clouds to radar observations and ground-based observations over large regions of the central US that have been roped out for this purpose by the Department of Energy. And we do that globally by comparing simulation results to constellations of satellites that are constantly looking at clouds and the signatures of radiation wafting off the planet associated with clouds. So that's the essence of the cloud problem. And again, it's encapsulated every 7 years by the IPCC in their summary documents. Another consequence of this is climate prediction. So when economists and policymakers make scenarios of how much CO2 we think humanity will emit under various what-if scenarios. Under the same scenario, under the same what-if, climate models produce a range of warming results. So the same human activities, some models say will cause 4 degrees of warming, other models say will cause 7 degrees of warming. One of the major reasons for disagreement are different predictions about what clouds will do. So here's another quote from the IPCC illustrating that. The main factor causing spread in model predictions are cloud feedbacks. Okay, that's the context, that's the problem. I'm working with a new way of simulating the atmosphere that does clouds differently. So I'm one of a handful of people studying this approach, which is called a multiscale modeling framework. So rather than having one global model resolution, we have 2 resolutions. This model works instead of statistically approximating clouds on the planet, it explicitly resolves clouds in small interior models that actually create clouds that live and die and grow. It's unaffordable to cover the whole Earth with this resolution, but this approach kind of works like opinion polling. So you take a small sample of the population and pretend it represents the state. Okay, so we can afford to explicitly represent cloud physics in small subdomains, 10,000 cloud resolving models hanging out inside of a global climate model. So this approach is called multiscale modeling or cloud superparameterization. It was invented maybe 12 or 13 years ago, and we're still studying it. It takes a lot of computing power to use this approach. It's about 200 times more expensive than the usual techniques. This is one of the machines I work on in Tennessee. It's got about 130,000 computing processors. I use about 10,000 at a time. So I'd like to give you, just as an example, a flavor, a taste of some of the things we do in my group with this kind of technology. Something related to missing weather patterns. So recall, one of the age-old problems in climate models are missing weather patterns. Let's talk about the Madden-Julian oscillation. MJO, acronym alert, okay? MJO. What is it? It's this thing. It lives in the tropics. It's this oscillation that modulates rainfall and extreme weather every 30 to 70 days. It's the most energetic cycle in the atmosphere behind the monsoon. It's this thing. I showed you an animation of it happening. It's when convection gathers into giant planetary scale complexes that move slowly from the west to the east. This is the MJO. It's a fascinating thing in basic atmospheric research because people are still arguing over how it works. This is kind of a diagram about the vortical structures associated with the MJO. And a consensus theory of how it ticks is still kind of a holy grail in tropical atmospheric dynamics. So various mathematicians have ideas for how it might work, but they're hard hypotheses to test. It's hard to currently select between competing theories. And one of the reasons it's hard is because we don't have numerical models that capture convincing MJO signals to test hypotheses. Okay, one more acronym, CAM. CAM is a US homegrown climate model that's the most widely used climate model in the world. I use a souped up version of CAM that contains cloud resolving models. Souped up cam, SP cam, okay? All right, this is the new cam, that's the old cam, all right? Lots of people use this climate model. This is kind of a confidence check. This is observations here, don't worry about the details, but just sort of compare these two columns here. This compares the dozens of real occurrences of this event in the tropics and looks at the detailed dynamical structure of the event in thermodynamics and dynamics. And this model can reproduce an amazing match to observations. It's one of the sorts of sanity tests against data that we use to convince ourselves a numerical model is capturing an important missing weather pattern. And so once we have confidence like this, we can proceed to do something scientifically useful, taking a high degree of freedom model that, unlike mathematical, simplified analytic models, makes minimal assumptions about how the MJO works, and use it to test competing hypotheses to advance basic atmospheric science. So it's like a virtual laboratory. This is the MJO. This is a visualization of the statistical signature of the MJO in my model, which you can observe in much more detail than real data. And we can sort of use this virtual laboratory to test ideas about MJO physics that are in debate. So let's consider a hypothesis. Okay, what does this mean? All right, here's some jargon. Mesoscale organization is important to the MJO. What is mesoscale organization? It's this. Convection is not always popcorn-like, little puffy, floppy clouds that are kind of scattered and look like static. Often convection is organized into systems that look like this. These are called mesoscale convective systems. They're sort of conglomerations of convection with a characteristic structure. They are organized in ways that affect the statistics of turbulence. It becomes more two-dimensional. And a property of two-dimensional turbulence is that, counterintuitively, it can transport momentum from small scales to large scales. So you could imagine how these sorts of ideas might relate to the physics of a very large-scale planetary disturbance. It's also important because it changes the way that convection heats the atmosphere. All clouds heat the atmosphere by releasing latent heat. But organized storm systems heat the upper atmosphere and cool the lower atmosphere because of all the descending ice virga, which evaporates. So these are reasons why people have suggested this hypothesis in the literature. And it leads us to an expectation for our souped up cam that somehow its Madden-Julian oscillation, its rare missing weather pattern, depends on having resolved this mesoscale organization process. That's something we can test by using our virtual laboratory of the MJO and performing hand-of-God experiments that you could never do in nature. This is a picture from a Facebook group called the Cloud Appreciation Society, which I recommend if you're into clouds. That's the cloud hand of God. Okay, so what I mean is that in a virtual world, we can control this process of mesoscale storm organization by doing something very artificial. The embedding cloud-resolving elements inside my multiscale atmospheric model are intentionally designed to be large enough for storms to organize. Okay? They're 128 kilometers long. I know that storms organize inside them because if I just visualize the contents of the cloud-resolving models, I can see these classic archetypal structures of organized storm systems. Do they matter to the physics of the Madden-Julian oscillation? We can test this by just artificially restricting the size of each of these cloud-resolving elements. So they're too small for storms to ever organize. If the hypothesis that this process is critical is true, that should disrupt the MJO signal. So let's look at the results, okay? To look at the results, you got to understand this picture. It's not too hard to understand. Imagine you're a satellite looking down at that region of the tropics near Bangladesh, watching many instances of tropical weather happen. And then you summarize everything in your movie with a picture. This is that picture. It organizes everything you see by time scale. So these are things getting slower as you move down. And spatial scale, disturbances that get larger. Eastward moving things go here, westward moving things go here. This here is the MJO. It's a really large oscillation that moves to the east very slowly, and it's the biggest signal on the graph. Okay? So in our control experiment, this is the MJO. Let's see what happens when we artificially, using the hand of God, restrict storm organization. Okay? Here's data. Here's the control experiment, and here are my tests. So take a look. What do you think? This is the MJO here. This is the MJO in the control experiment. This is the MJO in the tests. Has it vanished? No, it's still there. It's inconsistent with the hypothesis. So these are the sorts of things you can do in a virtual laboratory that are really useful for ruling out or ruling in competing mathematical theories about what's actually important to the MJO. This is a model that made minimal assumptions about the MJO, produced a convincing one, and is insensitive to restricting mesoscale storm organization. So that's just a taste of sort of some of the basic atmospheric science research we do in the group. It's an example of an insensitivity to a process that's relevant to some paradigms for how this disturbance works. It's opening doors for computationally accelerated superparameterization because the lion's share of the work we do are in these cloud resolving elements. So when you shrink them, you're not doing as much work, your model runs faster. That can be useful. We've done other experiments that have produced sensitivities. Here's an example of a speed up. So this is a plot of time versus distance. So the slope on the plot shows you the speed of the MJO. And this is another experiment I performed a year ago where we found something that really affects the MJO. When you vary it, the MJO speeds up. Okay, that's a lot of graphs. I'm sorry. Okay, I'm sorry. I can't help myself. So in lecture, what we do when we've gone through too many graphs is rap about climate. So I promised I would do that here. So we're going to do it. Okay. Let's take a breather. Let's see if this beat works. So it's a hobby of mine. I like to rap about the climate system. So this rap goes down well in California because it's about why it doesn't rain in the Orange County. So why doesn't it rain in the Orange County? We talked about it earlier. You know, the Earth is a planet in a vacuum. It's heated more at the equator than the pole, and that excites circulations like the Hadley cell, which transport energy polewards. We live at the descending branch of the Hadley cell, which brings dry air down and keeps it from raining. And at the same latitudes that we live, all the deserts occur for the same reason. So the reason it doesn't rain in the OC is because, you know, this Hadley cell, which is coupled to deep convection in the tropics, keeps us dry. So now in rap form. All right. Okay. Bear with me. All right. Deep convection in the tropics drives that whole global motion of the air that you've been copping in between when jokers joking. You know they snorkeling in oceans, checking liquid flowing motions from the force that got air going. Best believe my science tight. I'm talking differential force and different solar radiation. The latitudes absorbing. Had the fact the Earth be spinning, Hadley circulation soaring. Up in tropics, down in OC. That's the reason it ain't pouring. All right. All right, thank you. Okay, thanks. Seriously, hopefully you're awake again. Okay, so I want to tell you about two other things. Okay, so I want to talk about climate change prediction and how this new way of simulating the atmosphere is changing some of our perceptions of how things might change with climate. So for instance, now that it can be simulated in a global model, the response of the Madden-Julian oscillation, which affects lots of people living in the tropics, to elevated carbon dioxide can be studied for the first time. And this is a figure from an interesting paper published by a colleague in PNAS last year that shows if you take this souped up climate model and run it in the current climate and then quadruple the CO2, what happens to the rainfall associated with the Madden-Julian oscillation? Okay? So here's the rainfall associated with the MJO. It mostly affects people in Bangladesh, India, Southeast Asia, the Philippines, and Australia. And after quadrupling CO2, wow, there's a big sensitivity. If you quantify this sensitivity, it's interesting. It's actually bigger than we expect for most weather patterns. It's about 10% amplification per Kelvin. And unlike most weather patterns, which become more intense and less frequent, this thing becomes more intense and more frequent, according to the souped-up CAM. Really tantalizing and interesting prediction. If it's true, it's something that's going to really matter to lots of people living in this part of the world. This is an example of a typhoon that flooded Bangladesh in 1991, in which 150,000 people were killed, and it caused $1.5 billion of damage. The Madden-Julian oscillation is associated with extreme events, so if it amplifies a lot, then we should be bracing for more of this in the future, and perhaps more than we expected. So this souped-up CAM also captures extreme weather patterns closer to home as well. This is an exotic form of rainfall that happens in the central United States breadbasket during the summer. You're going to see an animation from space of 2 days of satellite imagery that represents something that commonly occurs. So here's Baja down here, Florida over here, the Great Lakes up here, so this is the central US. And the colors show cloud systems forming in the middle of the night when the clocks point up. It's unusual for convection, and they're massive. These systems are massive. These deliver about half of the rainfall to the US in the summer. Here's a picture of one spanning multiple states. They're huge. They're hundreds of thousands of square kilometers large. They're called mesoscale convective complexes. They're another missing weather pattern. These have been absent in most climate model simulations and predictions of the future because they're hard to simulate, just like the MJO. They depend on the detailed physics of clouds. Here's a picture of one on the horizon forming. They form at nighttime and live through the nighttime. Those who grew up in Oklahoma may be familiar with the fact that it tends to rain most heavily in the middle of the night, which is unusual. It's unlike most parts of the world. It takes exotic convection to do that. And these are another form of convection that are associated with damaging events like lightning and strong wind gusts. So just like the MJO, now that we can begin to simulate this sort of a signal in a global model, we can analyze its climate sensitivity. And what are we learning? So this is a postdoc in my group, Dr. Gabe Cooperman, who's quite interested in the central US. And he published this result last year, which I think is quite interesting too. So here's a signature of these storms in the central US in the current climate and after quadrupled CO2. So we're again seeing sort of a striking sensitivity in the amplitude of extreme weather, getting more extreme. In fact, we see this no matter where we look when we use the souped-up CAM. Okay? These boxes here represent different regions of interest, and the blue lines show the usual model answer. The dark line is the current climate, the light line is the future climate, and there's a boost in the most extreme rainfall events, shown as a shift in this tail to the right. The red lines are the souped-up version of the model, and the shift is bigger, no matter where we look. If we look in the whole northern hemisphere, we see a big shift. If we look over Southeast Asia, we see a bigger shift in the souped-up CAM than the regular CAM. If we look in the US eastern seaboard, we see a bigger shift, and West Africa. So this new simulation technology is beginning to capture stronger extreme rainfall application with climate change, and that's actually something we expect from basic theory. This is fixing a problem that we know existed in previous climate models. There are reasons to think that convective extremes ought to scale at about 7% per Kelvin on average. So it's suggesting that some of these advances in climate simulation may help improve the fidelity of predictions for adaptation and preparing for the future. These may have economic benefits and social benefits. Model mergers in the past have done so, at least. So for instance, once upon a time, atmospheric models were not coupled to ocean models. And in the 80s, this was done. And after some tinkering, out came El Nino forecasts that had some useful skill that was useful for planning on a 3-month time scale. If you see something brewing in the ocean, some predictive skill in planning where to redistribute wildfire response resources with a bit of lead time. And there are reasons to think that perhaps there may be benefits from these new flavor of multiscale model mergers where embedded explicit convection is being coupled to atmospheric models. And we're seeing glimmers perhaps of improved predictability of the Madden-Julian oscillation as well as the sensitivity of severe weather to climate change. Okay, I want to talk about one more thing. This is my most exciting project that I'm really fired up about right now. And it's about the biggest cloud problem of them all. So we happen to live right next to one of the most climatically important cloud decks in the planet. So, the marine layer, May gray and June gloom. These low clouds that waft in, that are offshore, are actually parts of huge planetary mirrors that extend for hundreds of thousands of square kilometers. If you've flown from here to Hawaii, you've seen this out your airplane window. These low clouds, we live at the edge of a low cloud deck that covers a planetary, a huge scale. And it's not just off the coast of California, it's off the coast of Peru. There's another one of these things, low cloud deck. It's off the coast of Africa, there's one. Wherever there's cold sea surface temperatures on the western boundary of continents, these things like to happen, okay? They're important because they act like giant mirrors that cool the planet. They're really bright. If you look down on them from the airplane, it's hard to look because they're reflecting so much solar radiation from the planet. And they're important because their physics are exotic and ticklish. We can see that because this is a picture of the low cloud deck, and you see these linear lines. That represents the clouds being sensitive to just a small perturbation from diesel particles coming from shipping lanes. So these clouds are known to be sensitive. Some people think you might even be able to intentionally geoengineer them to make the giant mirrors artificially brighter to compensate for global warming. That's a controversial idea. But they're really important because they are clearly the cause of our current uncertainty in model predictions about the future. This graph shows that if you sort today's climate models by how much global warming they predict for 2100 and ask why, it turns out that the models that produced the least warming are those that predict that the low cloud decks get bigger, the planetary mirrors expand and buffer global warming with a bit of added solar reflection. And the models that produce the most warming do so because mostly because they predict the low clouds are going to contract. And just like the ice albedo effect, reveal darker ocean that absorbs more solar radiation. And so here's another quote from the IPCC. Uncertainty in the sign and magnitude of the cloud feedback, which is the biggest uncertainty overall, is furthermore mostly due to uncertainty about low clouds, the sorts of clouds we live next to offshore. So think about that next time you look at those clouds. They're some of the most climatically important clouds on the planet. So the elephant on the table is that all global climate models, even my souped up model, unsatisfyingly approximates low cloud physics. They're too hard. They're too hard to simulate. The reason they're too hard is because, believe it or not, the properties of this macroscale cloud deck are controlled by eddies that are tiny, on the scale of 20 meters vertically and 250 meters horizontally. Okay? Mixing by turbulent eddies of these scales is known to control the macrophysics of low cloud physics. Okay? So that seems like a computational grand challenge, that resolution. But my work on superparameterization has taught me that if you target your atmospheric algorithm to the current computing architecture, you can afford more than might seem possible. So one idealization that's made in the superparameterization approach, which is artificial but intentional, is for these embedded cloud resolving elements to be periodic laterally, which means that clouds that go out here come back in here. Okay? So each of the tens of thousands of embedded cloud resolving models are independent from each other. They interact infrequently through their interaction on the exterior planetary scale, but practically it means that the lion's share of the calculation, which is interior to these cloud resolving models, can be done perfectly scalable on a large supercomputer. So that allows you to take advantage of a larger fraction of a supercomputer than a normal climate model can. Scalability. So there's this scalability issue with software engineering, and then there's also the fact that the balance of computation is shifting really fast right now. We live in interesting times for supercomputing. Here's an example. This is the machine I used a few years ago. It had 130,000 processors on it. I was only able to use 400 to 10,000 at a time, just based on limitations of my code. But there's room for improvement in the code, and the computers are improving too. This is a new system. It's got 5 times as many computing processors, 500,000. And it's got thousands of new things we've never seen before called mics. I'll talk more about them in a second. Here's another one. This is from the Department of Energy. I'm hoping to get access to this soon. It's got, again, 3 times more than I'm used to, 300,000 processors and thousands of GPUs. These mics and GPUs are new things. They're coprocessors. Supercomputers have hit energy limits where the power grids are no longer big enough to allow supercomputers to get more powerful by just getting larger the way they used to. Now, there are energy limitations that demand the only way you can increase your flops is by retrofitting supercomputers with unusually low energy horsepower. And that's available cheaply in graphical processor units where video gamers have driven down the cost of certain classes of computations. If you can coerce your scientific code to take advantage of that, then you can afford more than you thought. And Intel has realized this, and they're fighting with NVIDIA and developing their own coprocessor that doesn't require as much software engineering to unleash, but may give you some of the same benefits. So we as a community haven't really figured out how to take advantage of these revolutions in supercomputing, but the possibilities are amazing. I think there's lots of computational room to sidestep things we thought we had to approximate. And so my most exciting project right now is to take advantage of some of these technological advances to update my cloud resolving models. Right now they look like this. They're about 130 kilometers wide, but unsatisfyingly for low clouds, they have coarse horizontal resolution, 4 kilometers. Okay? That cannot capture low clouds. So our plan, and it has about 30 vertical levels. So our plan between us is to update these cloud resolving models to look like this. So they'll be 32 kilometers wide with a 16-fold increase in horizontal resolution, down to that important scale of 250 meters horizontally. And so much vertical resolution where the low clouds live at the bottom of the atmosphere that you can't even see it in this picture. I have to zoom in 2 or 3 times to bring it out because we've increased the vertical grid. So the point here is to target the eddies that we know from explicit simulation control the macrophysics of low clouds, to build a global system that can explicitly capture even low clouds and nonetheless allow them to interact with global climate change. So this is an exciting new result from a postdoc in my group who's starting to do this and seeing some glimmers of hope. This is off the coast of South America at several grid points where low clouds exist in nature. And it's demonstrating at each of these grid points, each of these horizontal locations, the vertical time evolution of some pilot tests we've done that show the beginnings of a low cloud deck beginning to form. It's not dense enough yet. It's not, it's a existence, not a success yet so far, and we're working on it. But I'm really excited about it because, I think this is a really important climate problem. We live next to one of the most climatically important cloud decks in the Earth system. People in the central U.S. care about how much the global average temperature will rise for the same reason that people in Bangladesh care about it, Extreme weather events scale with global climate temperature at 7% per Kelvin or even as much as 10% per Kelvin for the MJO. And how much the global climate warms really depends on low cloud feedbacks. And so we're hoping within the next couple of years to have the first simulations that allow low clouds to interact explicitly with climate change and hopefully give a more satisfying, less approximate answer to the question about what they might do in the future. So with that, I'll leave it and take your questions, and thanks for your time.
So I'm going to take advantage of being dean and ask the first question.
Okay.
So you talked a lot about making long-term predictions, but what about just predicting the weather next week?
Right, so their physics really bites you. You're right. So, weather is inherently unpredictable beyond 2 weeks, regardless of how good your model is. Just due to the initial condition sensitivity of a chaotic system.
So the
climate can be more predictable, though.
Problem is still unsolved.
Right. Yeah. Climate can be more predictable because it depends on energy fluctuations. So for the same reasons we can predict it's going to be warmer in the summer than it is in winter, we can predict some elements of climate change. So the predictability of weather is not, tell you about the predictability of climate. Yeah.
It seems to me that when you create a model, then you need to test it by securing data about the clouds and the weather.
Absolutely.
I can't imagine how in real time you can collect data. You have a plane flying through clouds, and it measures whatever it measures.
Yeah.
But how how do you get the tens of thousands of data points that would be required for a 250 meter by whatever
Yeah.
bit of space? How do you do it?
Well, so there are,
Why don't you restate the question?
Oh, sure, yeah. So the question is, how do you decide whether these models are working, right? What's the validation strategy? It's a great question, right? And especially at these fine scales, how do you decide whether things are working well? So I'll try not to take too long. We could talk about this for hours. One thing we have to our advantage are satellites that have really powerful radiative constraints on vertically integrated properties. So for instance, over low cloud regions, there are microwave radiometers that can tell us with reasonable accuracy the vertically integrated liquid water content. And we know that liquid water from flying airplanes is located within the lower part of the atmosphere. Our intuition for what tiny scales control that liquid water content comes from explicit simulation of small patches of atmosphere that have shown over the last decade that to get independent modeling centers to produce convergent answers, this is the resolution required. So it comes, but ultimately our validation strategy for this model will be to perform sort of weather hindcasts. Weather hindcasts with a typical climate model will instantly produce collapse of low cloud signatures such that you can't even satisfy the easily detectable vertically integrated constraints from space. But in our pilot tests of weather forecasts, we're looking to see whether we can produce the right brightness of these clouds, which would reflect the appropriate liquid water content, which would further reflect a convincing eddy boundary layer interaction. Does that answer your question? Or? Okay. The point is we have amazing. Yeah, sorry, I get lost in the trees, but we have amazing satellites. We actually live right now. NASA has invested in the best generation of cloud detecting satellites that the planet's ever seen. And so we have really good constraints from space on problems with clouds, certainly enough to know that climate models are failing with certain key problems with clouds, and enough to tell whether we've succeeded in beginning to resolve some of those problems. So that's the first tack.
Yes, thanks, Ken. Question, Professor Pritchard. About 10 years ago, there was a major issue in the measuring the solar load in the equator near the oscillation, the Glimmer oscillation. And it was about 70% of what they had expected. Instead of 1 kilowatt per square meter, there was only like 600 watts or 700 watts per square meter. And they said, and again about a decade ago, because my database is a little bit short, that the problem was due to the dust coming off of India and Bangladesh coming in and lowering the solar load on the surface, which then powers the entire global area that goes up towards West Africa and, of course, the Sahara Desert. Has that been resolved? Is that what it was, or is there something else wrong in that?
Oh, I mean, yeah, that's an interesting question. It's beyond my expertise. I mean, it is certainly true that dust plumes, such as I showed you a picture of, that get blown out over the Sahara, can affect the solar radiation budget at the surface. And you can even see the consequences of that being traced out in cloud formation in that satellite picture. And it's certainly true that simulating those sorts of dust-climate regional interactions is another challenge. But yeah, I guess I'm not aware of the specific observational discrepancy you're talking about, and I'm not aware of the answer to your question.
The next question then, what are you putting into your model as the solar load per square meter of the ocean? What are you doing?
So the model receives boundary conditions exterior to the planet from the known brightness of the sun.
Right.
And that's very well known because we have satellites that point at the sun from orbit. And then what happens interior to the planet is a function of the model's predictions. So if the model contains physics to loft dust interactively and blow it out over the ocean, then it is, with sufficient vertical resolution to capture a realistic attenuation of the solar beam at the surface, then this is in theory something that one could simulate. An obvious problem that would come up is clouds, though. I showed you a picture that showed that one of the main mechanisms that actually lofts the dust into the Atlantic are large organized cloud systems. And those are inherently difficult to capture. Those are often missing from climate models. So you might imagine that the current generation of models could struggle with this mechanism, at least in the eastern Atlantic. Yeah.
So the dust model is still to come.
Dust models exist, and there are, people who work on dust models in our department. And I should say, I'm one of, one person in a department that has a really interdisciplinary faculty working on lots of other areas that are not, where they could be in climate models. And yeah.
Just a related thing, I just noticed in the paper the other day about some big volcano down in Chile has just had its third major eruption. Does that have an impact either regionally, or does it morph into a more global type of thing? I'm not even sure how big that was. I just saw a picture of it. It looked pretty significant. Obviously, you can't predict it.
I mean, volcanoes in general have clear climatic consequences. The 1992 eruption of Pinatubo caused a global cooling for a couple of years. And the sulfate particles that are naturally put in the stratosphere of volcanoes have been eyed by some geoengineers as a way to artificially cool the planet. So yeah, I think there's every reason to expect the eruption in Chile could have an effect on climate if it's large enough. I'm not aware of how large that eruption was or what we should expect.
Yeah, I wasn't able to get any details on it. I just saw a picture and it said it was the third major one. It looked pretty significant.
Yeah.
Terry?
First of all, I want to thank you for really helping me conceptualize the climate models and their limitations. Super helpful and really fun to see how our local weather patterns fit into that. I have lived in California most of my life, and I watched the marine layer shrink. And, I wondered if it was just me or just due to Orange County from the Bay Area, but no. I read that it really has shrunk. And so that's already happening. Is there any reason to believe that it would grow with climate change, further warming? It seems like we already have the data to show that it shrinks. And so that's one question. The second question is, do you have climate change models for dummies out there that I can share with my friends who are not physical scientists?
Great questions, thank you. Yeah. So first off, I'd love to know what you read. Our impression of the marine layer is a microcosm of the actual geographic extent of this planetary mirror that happens to butt up along our coast. And I don't know whether the paper you're referring to refers to what we see at the coast. So long-term trends in the properties of clouds are notoriously difficult to detect. The records are not long enough nor detailed enough to really draw trend lines through any cloud category, to my understanding, or if they are, they're dubious. And so a lot of our intuition for what to expect from what low clouds might do comes from high-resolution, limited area models that really, take a small patch of atmosphere, apply boundary conditions that will produce low clouds, and then perturb the situation with higher sea surface temperatures or reduced subsidence expected from reduced mass flux. So from those sorts of experiments, there are competing ideas about what will happen to low clouds. Some mechanisms can be invoked to explain why they should thicken and increase, which would offset global warming, and other mechanisms suggest they should thin, which would amplify global warming. So it's really sort of anyone's guess. Until such physics are allowed to interact freely with all the global modes of climate variability, it's sort of an open question. But it's a really interesting and important question, and I agree it's great that we live next to one of these super important cloud decks. A really accessible book about climate modeling, I have to recommend Dave Randall's books. He has a climate primer. There's a primer series that was published by the National Academy recently. It's like a paperback, thin book that's about really water vapor and clouds in the climate system, and also a little bit about climate modeling. And then at a slightly more advanced introductory level, he's got a new textbook at the graduate level coming out this summer that I expect is going to be really well communicated. He has a website too with an online textbook about how climate modeling works under the hood. So David Randall.
One more question.
You showed us that the diesel tracks of the shipping lines affected the clouds, and also stated that this meant that possibly there was a way that we could affect the low cloud layer. Could you elaborate on that?
Sure, I'm not an expert in this field, and we have someone in the department who is, who you might like to talk to, Steve Davis. But my impression is that there are two strategies out there for potential geoengineering. One mimics volcanoes by injecting sulfur particles into the stratosphere to cool the planet to offset carbon dioxide warming. Another one has been proposed, based on the pictures you saw, to sort of spray nucleating particles into saturated but limited, nucleus-limited regions of the subtropics, and the idea being that maybe you could spark, you could artificially enhance the brightness of our planetary mirrors in those regions. I think that's a little more, there's a little more skepticism about whether that would work. For the same reason, there's large uncertainties in what those clouds will do to climate change. We have virtually no idea what they would do on a planetary scale to that kind of an intervention. And of course, neither of those issues address carbon, acidification of the ocean, and that raises lots of questions. But it's interesting, and someone may try it, and we, I think like nuclear weapons, we should study it and be cautious about trying it.
Okay, it's 9 o'clock, so thank you all for attending. I'm sure Michael will be more than happy to answer some more questions individually. So thanks to Audrey, Tatiana, Nancy, and their team for making these series happen.